Swayam Prabha. Digital India. Educated India.
Welcome to today class of nonlinear vibration. In this class we are going to continue what we have studied in the last class, that is of a flexible beam, or we are going to study the nonlinear dynamics of a flexible beam. Today class we are going to particularly study about different types of beam: elastic beam, viscoelastic beam and magnetoelastic beam. Last class we have derived this equation of motion using both the principle, that is Newton's second law, and also by using this extended Hamilton principle, and we have seen how we can solve for a system with principal parametric resonance condition. And today let us start with this combination parametric resonance condition. So, we have taken the same beam, so same cantilever beam, base excited cantilever beam with an arbitrary mass position. So, the mass is at arbitrary position. Putting this mass at arbitrary position, or by adjusting this mass, we can generate, or we can have the frequency of the second mode and first mode in such a way that it can have two mode interaction, or it may have three mode interactions also. So, in case of two mode interactions, we have continuing that thing. So, here we have taken this omega 2 by omega 1 equal to 3:1. So, this gives rise to combination parametric resonance condition, and here particularly we will be interested to see this periodic and chaotic responses in case of combination parametric resonance condition. So, here the base excitation can be written in this form, that is Z equal to Z0 cos omega t. So, here this omega in case of the combination parametric resonance condition, so omega will be equal to omega 1 plus omega 2. So, as we are considering near to this omega 1 plus omega 2. So, here we can use some detuning parameter also to consider the nearness of this external frequency to this frequency omega 1 plus omega 2. In addition to that, so we have taken this omega 2 nearly equal to 3 times omega 1. So, here also we will take one detuning parameter to see the nearness of this omega 2 to that of 3 times omega 1. So, by substituting this thing in the governing equation and proceeding as we have already seen in case of the method of multiple scale, we can get a set of first order differential equation. So, here also we have used this transformation, that is P equal to A cos gamma and Q equal to A sin gamma, or P1 equal to A1 cos gamma 1 and Q1 equal to A1 sin gamma 1, and similarly A2 equal to A2 cos gamma 2 and Q2 equal to A2 sin gamma 2, and taking this omega 2 equal to 3 omega 1 plus epsilon sigma 2 and phi, that is the external frequency, equal to, so omega 1 plus omega 2. So, this is nearly equal to, so omega 2 equal to 3 times omega 1. So, that is why phi equal to 4 omega 1 plus epsilon sigma 1. So, here either you can write this phi equal to 4 omega 1 plus epsilon sigma 1, or you can write this is equal to omega 1 plus omega 2 plus epsilon sigma 1 minus sigma 2. So, these are the detuning parameter. We can get this equation. So, this for this combination resonance we have say get a set of equation, and by putting these P Q or P dot Q, P1 dot Q1 dot P2 dot and Q2 dot equal to 0 for steady state, we can find the response, and also by perturbing these equations. So, writing this equation in this form, that is P1 dot Q1 dot P2 dot and Q2 dot, equal to, so we can write this equation equal to equation. So, then by perturbing this thing, so we can get the Jacobian matrix. So, by perturbing this equation, so let this equation is A. So, it is a function of, so this is a function of P1, Q1, P2, Q2 and system parameters like this sigma and other system parameters alpha 1, alpha 2 or beta 1. So, this coefficient of cubic nonlinearity, coefficient of this forcing function, it will be a function of all these things, forcing f and m and then alpha, beta and gamma. So, now perturbing this equation, perturbing this part, so we will get the Jacobian matrix, and by finding the eigenvalue of the Jacobian matrix, then we can study the stability. In this particular case, when we are studying the stability, then for the fixed point response. So, if the eigenvalue of all the Jacobian matrix are in the left hand side of the S plane, so this is the real axis, this is the imaginary axis. So, if they are in the left hand side of the S plane, then the system is stable, otherwise it is unstable. And at the bifurcation point, so we know we have the static bifurcation and dynamic bifurcation. So, we can have the saddle node bifurcation, then we can have the pitchfork type of bifurcation or these transcritical bifurcation and hop bifurcations in case of the dynamic bifurcation of the system. We can first see how we can obtain the multi branch fixed point response curve. So, these are the multi branch fixed point response curve we have obtained in case of a combination parametric resonance condition. Here it is plotted A1 versus phi. So many branches you can see, so many branches are present in this case. Here clearly you can see this bifurcation point. So, these 2 points, these are the bifurcation points. Similarly, here also we have bifurcation point. So, here also, so we can have bifurcation point for particularly this bifurcation point. You can recognize easily that these bifurcation points where there is a bend. So, or here, so where there is a bend and then change in stability. So, they are saddle node bifurcation point, SN bifurcation point, that is saddle node bifurcation point, and these bifurcation points, this point and this point. So, these are the hop bifurcation point, hop bifurcation point, and this is saddle node bifurcation point. So, we have a combination of hop and saddle node bifurcation point in this case for different value of the system parameters. Then after getting this response plot, so how you are getting this response plot? You can get this response plot by solving the set of equation, first order equation by putting equal to 0. The resulting equations are these algebraic and transcendal equation, and so you have 4 such equations. So, these 4 equations you can solve by using this Newton's method to find this frequency response plot. Similarly, so if you are interested, so you can plot the bifurcation diagram. So, here the bifurcation diagram is plotted in the phi and gamma plane. Phi is the frequency of external excitation and gamma is the amplitude of external excitation. So, you can see, for example, let us take this 1 and 2 curve, the curve marked with 1 and 2. So, below this thing, so you can find this point, below this thing always the system is stable. So, this 1 and 2 are trivial hop bifurcation point to the left and trivial hop bifurcation point to the right. So, this line shows the hop bifurcation point observed in the system. So, this line 3, the non-trivial hop bifurcation point in the right side, and the curve 4 shows. So, this is the curve 4. So, it shows non-trivial hop bifurcation point in the right side. 4 shows this SN bifurcation, that is the saddle node bifurcation point. So, 4 is the saddle node bifurcation, 3 is non-trivial hop bifurcation point right, then 5 is non-trivial hop bifurcation point left. So, 5, let you see where is the line 5. So, this is the line 5. So, it is the non-trivial hop bifurcation point towards left, and 6 is the 7 and 8, 6, 7 and 8 are the saddle node bifurcation point. so many bifurcation points you are getting. So, by changing the or by plotting all these bifurcation point in the phi and gamma plane. So, we can get the bifurcation set. So, this is the bifurcation diagram or bifurcation set, and by plotting this bifurcation set you can know the critical value at which the system can be operated. From this thing you can find where the system has to be. So, for example, in between 1 and 2 the system has, so as it is Hopf bifurcation point, as 1 and 2 are trivial state Hopf bifurcation point. So, clearly, so you can have periodic response in between 1 and 2. Similarly, between these 3 and 5, so 5 is also non-trivial Hopf bifurcation point. So, 5 is the non-trivial Hopf bifurcation point, and 3 is also the non-trivial Hopf bifurcation point. So, these two 3 and 5 are non-trivial Hopf bifurcation points. So, this is 3 and this is 5. So, in between also you can have this periodic response, and so within 2 and 5. So, you can have a set of periodic response. Some of them will have their root in the trivial state and some of them will have their root in the non-trivial state. So, due to presence of all these periodic response, so there may be a chance that the period doubling root to chaos or some other different type of root to chaos also can be observed in the system. This is a very critical system, though the system is very simple, that is, this is a simple cantilever beam with an attached mass and it is excited at its base with a harmonic force, but the system yield a number of bifurcation points, and we can see in addition to the fixed point response we have periodic, quasi periodic and chaotic response. Near this Hopf bifurcation point, trivial state Hopf bifurcation point. So, you can see there are, so for different value of phi, by changing different value of phi, so we can get different periodic response. So, you just see these are different periodic response, and here you can see at A equal to 4.3, then A is 4.3. So, B is phi equal to 4.35, then 4.37. So, you are going to increase the phi here. So, when you are increasing phi, so you can see the periodic orbit, that the orbit reduces. So, initially you have a very large orbit which contains the harmonics. So, due to the presence of harmonics, it is no longer the circular in nature. So, it contains harmonics. So, these bending and so these shapes are there or irregular shapes are there. Slowly by increasing this phi, so you can see as you are going away from the combination resonance condition, the shapes are getting more and more irregular shape, and at 4.92 you can see you have a periodic response, closed periodic response. So, it is plotted in P1 Q1 and P2 Q2. So, this shows the first mode and this shows the second mode periodic response. So, you can have this periodic orbit and with increase or with decrease in the phi value. Increase in the phi value, it will go from E to, so E highest phi value and A is the lowest phi value. So, it will decrease from E to A. So, by decreasing this frequency, so we can getting, so we are getting bigger and bigger orbits. Similarly, so here you can see clearly these simultaneous existence of periodic orbit near the trivial and non-trivial supercritical Hopf bifurcation points. Already we have seen, so it is in between we have this trivial state Hopf bifurcation point and non-trivial state Hopf bifurcation point, that is between 2 and 5. So, there are symmetrically, so you can see symmetrically 4 periodic orbits are there, and so there are 5 orbits, periodic orbits simultaneously existing, and by, so here you can see the transformation. So, from the equation PQ equation you can see under this transformation, so the equations will remain same, that means P1 Q1 P2 Q2. So, if you replace it by minus Q1 P1 Q2 and minus P2, or by q1 minus p1 minus q2 p2 or by minus p1 minus q1 minus p2 minus q2, the equation remain unchanged due to the presence of, if you have a square term, then q1 square plus q1 square and minus q1 square will be same. That is why due to the presence of this type, so these terms in that equation, so reduced equation, so you can see, so it is invariant under this transformation. As it is invariant under this transformation, so you can have, so 4 different type of response. So these are the 4 symmetric responses present in the system. So later you can see that the symmetry breaking, so by changing this system parameter, so we can see, so symmetry restoring crisis we can get. So the symmetry will restored in this type of crisis. So initial point, by taking these initial points, so you can plot these curves and you can see the symmetry restoring crisis. Already you know a crisis occur when a chaotic orbit come in contact with an unstable fixed point or unstable periodic response. So here we are getting the symmetry restoring crisis. So here another thing also you can see. So initially we have this torus or periodic orbit initially, then it converted to torus. So here you can see this torus and then this torus get breakdown. So we are getting the torus breakdown root 2, torus breakdown root 2 chaos. So initially we have a torus, then this torus get breakdown and finally it leads to a chaotic orbit. So by slightly changing the system parameters, we can get the torus breakdown root 2 chaos in this combination parametric resonance case. Similarly, you just see finally this is the chaotic final chaotic orbit after the torus breakdown. You can recall that we can get a torus. So if the response is quasi periodic, for example, in case of a quasi periodic response, so you can write your y equal to a sin omega 1 t plus b sin omega 2 t. Here this omega 2 by omega 1 is irrational number. This is irrational number. So if it is irrational number, so then we can get a quasi periodic response. Quasi periodic response. So these are in case of quasi periodic response, we can get the torus. So in case of torus, for example, so you have 2 loops. So if you plot the phase portrait, the shape will be like this. So inside you have 2 loops and they are connected by this. So if you draw the phase portrait, so the shape will be like this. This is the phase portrait, that is your y versus y dot. So now you can draw the Poincare section. So in case of Poincare section, so this y versus y dot curve will be a closed loop. So in case of Poincare section, so you can get a closed loop in case of the quasi periodic response or this torus. So this torus get breakdown by changing the system parameter and finally you are getting a chaotic orbit. So this is the final chaotic orbit in case of the torus breakdown. Similarly, we can have the intermittency route to chaos, intermittency route to chaos. So you can see initially we have this periodic response and this periodic response by changing the system parameter. So you can see this is converted to a chaotic response where this may revisit, this chaotic response may revisit the initial periodic response intermittently. So you can have intermittently the periodic response, some part of this thing will be periodic and then again it suddenly wanders and it can go to other orbits. So you can recall that initially we have 4 symmetrically placed periodic response. A chaotic attractor can be, so due to the presence of so many bifurcation point. So here a chaotic attractor or chaotic attractor may also exist, which can connect all these attractor, all these periodic attractor can form this intermittent root 2 chaos. So, this way we can observe this intermittency root 2 chaos in this simple system. So, you just see initially we have the periodic response, now it wanders, it moves from one place to another place, and we are getting this intermittency root 2 chaos in this case. So, this way we have seen many different periodic, quasi periodic and chaotic responses and the roots to chaos, that is 3 different root to chaos we have seen till now. So, we have seen the period doubling root to chaos, then this torus doubling root to chaos and torus breakdown root to chaos also, and we have seen this crisis, that is intermittency root to chaos also we have seen, and here also we have seen this symmetry restoring crisis. So, initially it was symmetric, and this chaotic response also it makes it to be chaotic, but this chaotic response is symmetric also. So, that is why it is symmetry restoring crisis, and further we have seen this torus breakdown root to chaos and intermittency root to chaos. So, let us see another example or another type of system. So, where we can take the 3 mode interaction. So, we have the same cantilever beam, same base excited cantilever beam, but with 3 mode interaction. So, 3 mode interaction means we have taken, so this phi, that is equal to external frequency equal to twice 2 times omega 1 plus epsilon sigma 1, and here we are taking for example this omega 1 is to omega 2 is to omega 3 can be taken in this way, 1 is to 3 is to 5. One can take 1 is to 3 is to 5 or 1 is to 3 is to 9. In this case we have taken it is equal to 1 is to 3 is to 5. That means, the second mode is nearly 3 times the first mode and the third mode frequency is nearly 5 times the first mode frequency. By using this detuning parameter, so we can write this phi equal to 2 omega 1 plus epsilon sigma 1, omega 2 equal to 3 omega 1 plus epsilon sigma 2 and omega 3 equal to 5 omega 1 plus epsilon sigma 3. So, here we can get 6 reduced equation. Previously we have taken only 2 modes. So, there we got 4 equations. So, in case of Zavordini and Nafe, so they have taken 1 mode only. So, they have the 2 reduced equation. So, depending on the number of modes you are considering, the number of equations, reduced equation will be increased. So, here as we are taking 3 mode interaction. So, here we have 6 reduced equations. So, one will obtain 6 reduced equation using method of multiple scale, which have to be solved to obtain the response and stability. Some typical chaotic responses are shown in the following slides. So, here only we are showing some very typical chaotic orbit. So, you can see the transition from the periodic to chaotic response via a period doubling sequence. So, initially we have a periodic response, then it becomes period doubling, then period doubling root to chaos. So, we have seen this thing. So, in the first figure you can see the escape of the trajectory from the trivial and non-trivial fixed point response to form a 2 periodic orbit at phi equal to 1.89 initially. So, this is the 0 0 line you can see. So, this is the trivial state and we have a periodic response. So, it is escaping. So, you can see that it is escaping from this one. So, escape of the trajectory from the trivial and non-trivial fixed point. So, it will come out and now it will form a 2 periodic orbit at phi equal to 1.89. So, here this is we have shown the 2 periodic orbit, and then if you change further this system parameter. So, it will lead to this period doubling root to chaos. So, chaotic orbit at phi equal to 1 point. So, this is 95 and then funnel shaped chaotic orbit. So, you can see a funnel shaped chaotic orbit at phi equal to 1.98. So, here you just see we have seen different type of chaotic orbits, like you have seen previously the Lorentz attractor or the Rosler curve. So, similarly, in the simple physical system, So, this is a simple physical system, that is a base excited cantilever beam. If we are considering different modal interaction, so we can see different type of chaotic orbits present in the system. Here again you can see simultaneous existence of quasi periodic and chaotic responses near the subcritical Hopf bifurcation point. So, we have a subcritical Hopf bifurcation point in 3 mode interactions. I am not showing you the fixed point responses, but you can go through the detailed paper. I will give you the list of papers from which all these things have been taken. So, these are part of my PhD work. So, here you can see simultaneous existence of quasi periodic and chaotic responses near the subcritical Hopf bifurcation point, phi equal to 1.828, gamma equal to 8 and nu equal to T2. So, phase portrait A, and you just see the time response here. So, you have a periodic response, slightly periodic, then it is wandering, and from the time response clearly you can see that this chaotic orbit is wandering between different fixed point responses. Okay. So, wandering trajectory between unstable fixed points. Here you can see, so this is a quasi periodic orbit, clearly this is a quasi periodic orbit. So, to know whether it is a quasi periodic orbit or not, so you can draw the Poincare section. So, this is the Poincare section plotted for this P2 Q2, and how to draw the Poincare sections already I have explained. So, you can take the lowest frequency or lowest not lowest frequency, you just take the lowest time period. So, taking the lowest time period means, so omega equal to 2 pi by t. So, 2 pi by t corresponding to lowest time period, you have the highest frequency. So, you can get the FFT and you can get what are the frequency present, taking the highest frequency. So, you can find what is the lowest time period. So, taking this time period you can sample the time response, and from that sample, so you can get all the points on the curve. So, by taking all these points, if you plot, then for a quasi periodic orbit, so it will be a closed loop. So, here clearly we have seen a closed loop here. So, due to the presence of this quasi periodic orbit, so you have seen the Poincare section to be in the shape. So, here what we have seen, so simultaneous existence of quasi periodic orbit and chaotic response. So, at the same value of phi, so you can see there we have the quasi periodic orbit and also the chaotic response. So, both of them are present simultaneously in this 1:3:8 resonance condition. You can see in details all these responses in the references what I will show you after few minutes. Let us take a simplified model. So, I have shown you a complicated model with internal resonance, that is 2 mode interaction and 3 mode interaction. If we take a simple cantilever beam also single link, so which can be used as a single flexible link with a payload. Let us take this system and let it is subjected to this base excitation in vertical direction. So, previous case we have taken a vertical cantilever beam. So, here we are taking a horizontal cantilever beam. By changing the orientation also your equation of motion will be different. So, here by using this D'Alembert principle, so you can have this is the equation of motion. So, this equation motion here now by applying this Galerkin principle, so you can see that it is reducing to this form, that is G double dot plus G. So, here previously I have taken Q and here it is taken G. So, this is the work of my PhD student Dr. Varun Pratihar, so who is now a faculty member at IIT Jodhpur. Using this Galerkin method, he has reduced this equation to this form, that is G double dot plus G plus 2 epsilon zeta G dot plus epsilon into alpha 1 G cube plus alpha 2 into G square G double dot plus alpha 3 into G dot square G. Here only single mode approximation is taken. So, by taking the single mode approximation, we can get these nonlinear terms, cubic nonlinear term. So, this part is the cubic nonlinear term and these two are the inertia nonlinear terms. So, in addition to that, so we have in this case you can see this term last term, that is phi alpha into omega square cos omega t. So, this is a forcing term. So, you just see it is not coefficient of this g. So, that is why it is this is give rise to an external forcing term, and for this part, that is epsilon alpha for omega square cos omega t into g square. So, into g square as g is the time modulation whose coefficient is a periodic function. So, that is why the system is a parametrically excited and also it is subjected to external forcing. So, it is a direct and parametrically excited system. As the temporal equation of motion contains many nonlinear terms and it is very difficult to find the closed form solution. So, one can go or use this perturbation method. So, there are several ways you can use this perturbation method, or you can use this harmonic balance method also. So, I will show you use of harmonic balance method in some other examples also. Also, you may use this method of normal form or Lindstedt-Poincare technique in this case. So, using this method of multiple scale, so we can see we have two different resonance condition. So, one is the simple resonance condition and second one is the simple resonance condition when, so this omega bar equal to coefficient of g, that is equal to 1, when omega bar equal to 1. So, this is known as the simple resonance condition, and also we can have the subharmonic resonance condition when omega bar nearly equal to 3, subharmonic resonance when omega bar nearly equal to 3. So, in this case, in case of simple resonance, so we can have two equation, two reduced equation. So, system has only non-trivial response. So, here you can see by substituting this a dot equal to 0. So, you cannot take a common from here, because this last term, that is half alpha 5 sin gamma, so does not contain a term. So, you cannot take a common to make it equal to 0. So, there is no trivial state and the system has only non-trivial response. So, by substituting a dash equal to 0 and gamma dash equal to 0, so you can have a equation. Similarly, for subharmonic resonance condition, the system has both trivial and non-trivial response, because here you can take a common. So, put a dash a dot equal to 0, by taking a common. So, this becomes minus zeta minus omega bar square alpha 4 by 8 a sin gamma. So, either a will be 0 or this part will be equal to 0. So, as a equal to 0 is a solution, a trivial state present in this system. So, also in addition to that, we have the non-trivial state. Trivial state means a equal to 0, that is the amplitude becomes 0. Now, we can plot taking all these system parameters. So, you just see here the length is taken to be 0.336 meter, and then moment of inertia I equal to 7.0610 into 10 to the power minus 12 meter fourth. So, you may note that the dimensions are taken very small. So, if you slightly vary the dimensions, the natural frequency, there will be large variation in natural frequency. So, they are very sensitive to the variation in the dimensions of the system. So, you have to take proper dimension system to get the required results. So, the Young's modulus is taken to be 1.94 into 10 to the power 11 Newton per meter square, mass density equal to 7830 kg per meter cube, and this damping constant C D is taken equal to 0.11 Newton second per meter square. So, you can see a typical frequency response plot in case of the simple resonance condition. So, here there is no trivial state. So, trivial state is not there. So, we have all the points are in the non-trivial state. So, now by increasing this frequency, so you can see we have a saddle node bifurcation point here, saddle node bifurcation point here, and it will jump from this B to C. So, you can observe a jump of phenomena in this case, and due to this jump the beam may break again. So, it will follow, then it will follow this A, B, C, and further increase it will go to D. So, there will be a jump here, but if you reduce the frequency, that is it will go from D. So, it will follow this path D, C, E, and so it will jump from this point. So, as this is a saddle node bifurcation point, so from here it will jump down to this lower branch. So, you can see this hysteretic effect, that means while you are taking the frequency upward direction, while you are sweeping the frequency, it follow A, B, C, D, where it will a jump up phenomena. So, while you are reducing the frequency, it will not follow the same path, but it will follow another path, that is D, C, E, and it will jump down to a point here in the lower branch. So, by changing the system parameter, so now for example, you just take this mass ratio, different mass ratio, and also different. So, you can take different mass ratio and also different amplitude of excitation, and one can plot. So, these bifurcation points, there will be only change in these bifurcation points, and one can get the required result by properly checking or properly finding the system parameters. In case of the subcritical subharmonic resonance condition, so you can see both trivial and non-trivial responses are there. Here you can see at 3, so omega bar equal to here. So, you just see exactly at 3, as you are taking omega 2 omega, here you are considering the single mode approximation and subharmonic resonance condition. So, your omega bar you have taken nearly equal to 3. So, as you have taken omega bar nearly equal to 3, that is 3 times the first natural frequency. The first natural frequency we have taken the non-dimensional first natural frequency equal to 1. So, that is why it is equal to 3 at 3. So, the system, this unstable branch and this unstable branch meet at this point, and we have this curve, and here. So, you have a clearly you have a saddle node bifurcation point, and with increase in this z value. So, for example, by increasing z or decreasing z, here we have decreased the z value. A in curve A, z equal to 0.1, and in curve B, so z equal to 0.01. So, it is decreased. So, by decreasing this thing, so this is curve A, this is curve B. So, the previous one frequency response curve m bar equal to 0.563 and z bar equal to 0.2. So, here z bar equal to 0.2, in this case z bar equal to 0.1, and in this case z bar equal to 0.01. So, that means for very less value of amplitude of external excitation, so you can have the trivial state. So, the trivial state and non-trivial state do not coalesces at this point 3. You have clearly a saddle node bifurcation point here, and by increasing this z bar, so you can see, so this point single saddle node point. So, this branch becomes it takes a different shape. So, here you can see you have a saddle node bifurcation point here, and also a saddle node bifurcation point, but this is unstable here. So, this way you can see different responses in case of a simple cantilever beam, base excited cantilever beam. So, there is no external load acting in the system. The response we have obtained, that is simple resonance condition and subharmonic resonance condition. But in the same system, so if we are applying, now let us apply a load P equal to P0 plus P1 cos omega t, that is one axial load if we are applying to the system. So, for example, this is in case of a follower force acting on a system. So, in that case the system response will be modified to this form, and by applying this Galerkin method, so it is reduced to this equation. So, here you just see in up to this thing the response becomes, the equation is same. Now, we have this epsilon term, that is epsilon alpha 4 omega bar square cos omega tau into g square plus alpha 5 omega 1 square cos omega 2 tau plus alpha 6 cos omega 2 tau into g. So, this term is similar to this Matthew-Hill type of equation, presents in Matthew-Hill type of equation, where this periodic term is coefficient of g. So, here it is coefficient of g square, and this term is the simple external excitation or direct excitation. So, this temporal equation of motion contain many nonlinear terms. So, that is why already you have seen. So, we cannot have a closed form solution here. So, here in this case if you go on deriving using this method of multiple scale, you can see. So, there are several resonance conditions. So, for example, so we have these 3 resonance condition in this case. So, the first case is omega nearly equal to 1 and omega 2 bar is away from 2. What is omega 2 bar and what is omega 1 bar? So, this thing you can see omega 1 bar. So, is coming from this external excitation omega 1, and here we can put. So, this axial forcing actually we can put this is omega 2. So, this omega 2. So, we have 2 frequency excitation in this case. So, previous case we have taken only single frequency excitation, that is base excited, but now we have 2 frequency excitation, that is base is also excited with a frequency omega 1, and we have applied an axial force at the end with a frequency of omega 2. As we have 2 frequency excitation in this case. So, we have this omega 1 bar equal to 1 and omega 2 bar is away from 2. Similarly, omega 1 bar is away from 1, omega 2 bar nearly equal to 2, and we can have simultaneous omega 1 bar equal to 1 and omega 2 bar equal to 2. There is no restriction in omega 1 bar and omega 2 bar, independently one can control these 2 parameters. So, that is why in first case you can take, one can take this omega 1 bar, that is base excitation nearly equal to 1, but this omega 2 is away from 2, due to this axial loading there is no resonance condition. Second case omega 1 bar is away from 1 and omega 2 bar is taken near equal to 2, and third case we have this omega 1 bar equal to 1 and omega 2 bar nearly equal to 2. First case so, we have this, these are the reduced equation. In second case we have this reduced equation, and in third case, so these are the reduced equation. So, system has only non-trivial response in this third case. So, we will see all these 3 cases some results it is there. So, taking these system parameter, similar system parameter. So, we can study these 3 resonance condition. So, in case of simple resonance condition you just see the response is like this. So, it is having the subtaining effect. If you can compare this equation to that of a Duffing equation, so you can see, so it has a subtaining type of response, and here again we can have the saddle node bifurcation point, and you can see at omega 1 around 0.8. So, if you see, if you take around 0.8, so it has 2 stable and 1 unstable response. So, that means the system has a bistable region along with the presence of a unstable fixed point response. So, to which branch it will go, so depends on the initial condition. So, that is why one has to study the basin of attraction. So, here we have plotted the basin of attraction in that case, and you can see. So, we can clearly, so these are 2 fixed point response, and this is, you can find this is the saddle node point, this gives rise to the saddle node point, and this and this. So, this is the, so this point is the replica of this one. So, that is at 2 and gamma equal to. So, in a gamma plane we have plotted. So, this is also a fixed point and this is a fixed point. So, this fixed point and this fixed point are the same fixed point, but with different gamma, and this is the at 0. So, we have the trivial. So, near 0 also we have a fixed point. So, this is exactly not 0, but a smaller value. So, another branch is here, that is near, this branch is near these 2. So, that way you can plot it and you can verify the basin of attraction, and one can plot the time response, and clearly one can observe that this beating type of phenomena is occurring in this case also. And for a different value of P0, for example, P0 equal to 1.67 or 0.167 and 0.333. So, P0 is, so this is higher value of P0. What is P0? So, we can see we are applying a force. So, this force is P0 plus P1 cos omega t. So, this is the fixed part of the periodic response and this is the time varying part of the periodic response. So, if the fixed part is increased, actually by increasing this fixed part, so we can increase the stiffness of the system, and due to that, so you can see the response, nature of the response changes. So, we can have the saddle node bifurcation point at different locations. So, time response and Poincare max, initially we have a periodic response. So, in the Poincare section we have only a single point. So, here you can see in Poincare section time response showing a fixed point. So, this way you can show the fixed point by using a Poincare section, and here you can see influence of amplitude of base excitation on the frequency response. So, this mass ratio equal to 2, P0 equal to 0 and phi equal to 0. So, in P1 bar equal to 0.167. So, in first figure this Z bar equal to 0.00372 and in second case Z bar equal to 0.00744. So, here this base excitation is increased, amplitude of base excitation is increased. So, thereby, so you just see the nature is remaining same, but the amplitude is slightly increasing. So, we have taken 3 points in this. So, one point it is 2 points are stable and one is giving rise to unstable response. So, in phase portrait Poincare section, so you can see this thing. So, here clearly you can see the basin of attraction in this type of response. So, depending on the, so clearly this is the saddle point. So, you can see different saddle points and these fixed point responses in this case. So, you can have a tri-stable region here 1, 2, 3. So, 3 branches are stable. So, you can get 3 stable branch, and so you just see this point and this, in the previous case this and the above point we are at the same place, that is for a equal to 2, but in this case, so this a point are different points. So, they are at different points and you can have 3 values. So, as we have 3 stable points, along with that we have unstable points also, 2 unstable point. So, 2 saddle point can be so found near here 1 and here 1, 2 saddle points also may be observed. So, previously we have taken a elastic beam. So, if we take a viscoelastic beam, so in case of viscoelastic beam, so the equation will be modified by replacing this I by I plus I1 E1 plus I E2. So, this E, that is the Young's modulus, will be a complex number in case of the viscoelastic material. So, in that case E can be replaced by E star. So, this E star also can be written by E into 1 plus I eta. So, one can write in this form, that is where eta is the loss factor, or one can write expanding this thing, this will be E plus I eta E also. So, here it is written in terms of E1 and E2. This part, this first part is the shear modulus, storage modulus, and this is the loss modulus. So, this is the loss modulus, this is the storage modulus, and this part is the loss modulus. So, this is loss modulus and other one is the storage modulus of the system. By putting this complex number E1 plus I E2, so you can see the equation is changed. So, now the equation becomes q double dot plus q plus 2 I epsilon eta 1 q plus epsilon alpha 1 q cube alpha 2 q square q double dot plus alpha 3 q dot square q plus I eta I epsilon eta 2 q cube. So, plus this nonlinear term and then this forcing term, direct forcing and parametric forcing terms are there. So, we can use this perturbation method for analysis. So, here we can have a simple resonance condition and subharmonic resonance condition like previous case, but here we have the loss factor instead of loss factor. In this case, loss factor is written in terms of eta, and this A dash equation and A gamma dash equation we can get. So, system has only non-trivial response, but in case of subharmonic resonance we have this both trivial and non-trivial response present in the system. So, taking the system parameter, you just see we can take the system parameter. Here we have taken a material with density 1190.2357 kg per meter cube, scaling parameter r equal to taken 0.2. So, you can see we can plot this response. So, due to the presence of this viscoelastic material, like this damping property is high. So, in this case we can get the maximum response amplitude less than that of the elastically excited elastic beam used in our previous analysis. So, one can see the steady state response and the time response. One can convert that thing to an equivalent system, equivalent Kelvin-Voigt model. So, this is the equivalent Kelvin-Voigt model. In the linear case, if you take the equivalent Kelvin-Voigt model, so this is the linear response curve, linear frequency response plot one can obtain. So, frequency response plot for an equivalent spring mass damper system. So, this is the equivalent spring mass damper system with Kelvin-Voigt model one can take. Now, the frequency response plot, one can plot this frequency response and can see. So, in the previous case you just see the response is showing similar to that of a nonlinear thing, nonlinear system, a system of a equivalent to a linear system, and the response amplitude is found not to be same as that in case of the nonlinear system. So, this one can avoid this linear analysis. So, one can avoid the linear analysis and perform the nonlinear analysis to actually find the response of the system. So, if we extend to the second problem, that is a viscoelastic beam with tip mass and this axially periodically applied axial load. So, or a follower load P S plus P d cos omega t. Here also equation will be same, but E will be replaced by this complex number. So, due to the presence of complex number, so you can see we have these three different equation. One is omega 1 equal to 1, omega 2 is away from 2, omega 1 bar is away from 1, and omega 2 bar nearly equal to 2, and this omega 1 bar equal to 1 and omega 2 bar equal to 2. So, this way we can have these three different resonance conditions. So, for these three different resonance conditions, so we have three sets of reduced equation. So, from the reduced equation it has been observed that while in simple and simultaneous resonance condition the system has only non-trivial response, in principal parametric resonance condition the system has both trivial and non-trivial response. So, here we are studying the principal parametric resonance condition also, because omega 2 you are taking nearly equal to 2. So, it will leads to principal parametric resonance condition here. So, for different value of delta, that is loss factor. So, you can plot the response plot and you can clearly observe by increasing this loss factor the response amplitude of the system decreases drastically decreases. So, by using this viscoelastic beam, so you can reduce the vibration of the system extensively. So, these are the basin of attractions also plotted in this case, and you can study the influence of P s, Z and M. So, you just see by varying the mass ratio, so you can control the vibration of the system. Also by changing different response amplitude, so the response of the system can be controlled in a significant way. So, here you just see, so you have a bistable region. So, but with this Z equal to smaller value, if you take smaller value of Z, the response changes and it is completely stable response throughout the frequency range. Similarly, here also you can plot the frequency response for different value of Ps, that static value, and previously you just see you have only the saddle node bifurcation point, but here in addition to saddle node bifurcation point. So, if you are considering principal parametric resonance condition, that is omega 2 nearly equal to 2 and omega 1 is away from 1. So, we have these pitchfork bifurcation points. So, here we have pitchfork bifurcation point and you can study the response of the system for different pitchfork bifurcation points. So, in case of simultaneous resonance, omega 1 nearly equal to 1 and omega 2 nearly equal to 2. So, we have a combination of this thing, but the trivial state no longer becomes stable and it is shifted, this curve is shifted and we can have this multiple branch. So, due to the presence of multiple branch, so one has to study the basin of attraction. So, another problem we may study, that is stability region of a magnetoelastic beam. So, instead of taking a elastic or viscoelastic beam, so if we take a elastic beam, but made up of these magnetoelastic beam. So, that means ferrous material. So, if it is made up of ferrous material, then by applying this magnetic field we can easily control the stiffness of this beam. So, we can control the stiffness of the beam, and in this type of system, for example, let us apply a magnetic field B 0 equal to B m cos omega t and also a load of P equal to P s plus P d cos omega t. You can see the reduced equation, you can see the equation reduced to this form. So, here this term is due to the magnetic field. So, taking this Galerkin method, single mode Galerkin method, so this equation is reduced to a very simpler form, that is to that of a Matthew-Hill type of equation, that is u double dot plus 2 epsilon mu u dot plus u equal plus epsilon into alpha 1 cos omega bar tau minus alpha 2 cos 2 omega 2 tau into u equal to 0. So, this is simply it is reducing to that of a Matthew-Hill type of equation. So, here different resonance conditions can be considered, omega 2 nearly equal to 1 and omega 1 away from 1, omega 1 nearly equal to 1 and omega 2 away from 2, and both omega 2 nearly equal to 1 and omega 1 nearly equal to 2. So, in first case it is the principal parametric resonance condition. So, you can study. So, where this omega 1 equal to 2, omega 1 equal to, this is away from 1. So, that means we can take it nearly 2 and omega 2 is away from 1. So, we can get this resonance condition. So, here you can get a closed form type of equation. Similarly, for simple resonance condition, so you can get a closed form solution. So, as the equations are simple, so you can get a closed form solution, and from that thing you can plot this instability region. So, in the omega by omega L square beta B r by B c square B critical square. So, this is the curve one can find the instability region. So, outside the curve the system is stable and inside the curve the system is, or inside these two curves the system is unstable. So, this way you can plot the stability diagram. So, you just see the stability diagram. So, these are the critical value. So, these are the critical value below which the system, whatever value of B omega you apply, the system will be stable. So, one must find all these critical value below which the systems will be stable and apply that concept to control the vibration of the system. Similarly, for different parameter it has been plotted. So, if you take this same magnetoelastic beam and apply this magnetic field instead of applying axial load, so with a tip mass you can have this equation motion. So, in this equation motion you can study, you just see same different type of resonance condition. In this case you just see this equation. So, here this is the direct excitation, the second term this is the nonlinearity with nonlinear term is there. So, parametric excitation, and the third term is a parametric excitation term. So, we have these are the reduced equations you can get for different cases, and you can study similarly. So, you can study the frequency response curve, and here you can see how with varying this magnetic field and other parameters. So, we can have the response of the system. So, clearly you can see you can control the vibration of the system by applying different magnetic field. For example, this magnetic field 0 magnetic field, there is no magnetic field, this black curve is there. Then this one, the middle one is with Bm equal to 0.3, and when you are increasing Bm to 0.55, you can see you can control or you can reduce the response amplitude by 5 times. So, by using this magnetoelastic beam and applying suitable magnetic field, so you can control the vibration of the system. So, these are similarly one can plot this basin of attraction and study the system. So, these are detailed literature on which this today's presentation has been made. So, the work, so this is the part of the work is my PhD student Dr. Varun Pratihar. So, Varun Pratihar and Dwivedi, so parametric instability of a cantilever beam with magnetic field and periodic axial load. So, this is published in Journal of Sound and Vibration. Then Varun Pratihar and S.K. Dwivedi, so nonlinear dynamics of a flexible single link Cartesian manipulator. So, it is International Journal of Nonlinear Mechanics in 2007. The third paper is nonlinear dynamics of a flexible single link viscoelastic Cartesian manipulator. It is also published in the same journal, International Journal of Nonlinear Mechanics. Then nonlinear vibration of a magnetoelastic cantilever beam with tip mass, Journal of Vibration and Acoustics, this is ASME journal. So, there are some other papers also. Also you can refer this work by this R.C. Kaur and S.K. Dwivedi. Professor R.C. Kaur was my PhD supervisor of IIT Kanpur. So, nonlinear dynamics of a slender beam carrying a lumped mass with principal parametric and internal resonance. So, this was published in Nonlinear International Journal of Nonlinear Mechanics. Then nonlinear dynamics of a slender beam carrying a lumped mass under principal parametric resonance with 3 mode interaction. So, this is published in International Journal of Nonlinear Mechanics. Then nonlinear response of a parametrically excited system using higher order method of multiple scales. So, that is published in Nonlinear Dynamics. Then dynamics of a slender beam with an attached mass under combination parametric and internal resonance, periodic and chaotic response. This is published in Journal of Sound and Vibration. Dynamics of a slender beam with an attached mass under combination parametric and internal resonance. So, this is part 1. So, steady state response, this is also published in Journal of Sound and Vibration. So, some other papers are like this nonlinear dynamics of a cantilever beam carrying an attached mass with 1:3:9 internal resonance, that is published in Nonlinear Dynamics. Simultaneous combination of 1:3:5 internal resonance in a parametrically excited beam mass system. So, this is International Journal of Nonlinear Mechanics. Nonlinear response of a parametrically excited slender beam carrying lumped mass with 1:3:9 internal resonance. So, advances in vibration engineering. Then simultaneous combination principal parametric and internal resonance of a slender beam with lumped mass 3 mode interaction. So, this is published in Journal of Sound and Vibration. So, you can refer all these papers for understanding more and more of this how a slender cantilever beam can be used for generating different type of responses, fixed point response, periodic response, quasi periodic response and chaotic response. So, next class will extend this idea to develop an energy harvester by adding this piezoelectric patch to this cantilever type base excited cantilever type of beam. So, thank you very much.